Everyone, in control theory we are going to see about what is observable. So the system is x dot equal to a t of x, and our observation is y of t equal to h t into x of t. This is said to be observable when the pair, this is said to be the pair of h of t and a of t is observable on the interval of 0 to t. If y of t, we know that y of t is h of t into x of t equal to 0 means this implies that x of t, if y of t equal to 0 means x of t also 0. Then x of t can be written as x of 0 equal to x naught or 0, so whatever it may be. So if y of t equal to 0, x of t equal to 0 means the system is said to be observable. Okay, then we are going to the proportion one. The proportion one is otherwise known as the necessary and sufficient conditions for observable. So the given statement is, let x1 to xk be the vectors in R power n matrix, and let x1 of t, x2 of t, xk of t be the solution of the particular particular vectors, and of the solutions of the systems. So x dot equal to a of t into x on the interval 0 comma t, and each xi of 0 equal to, we know that xi of 0 is nothing but xi. So with I equal to up to 1 to k, because we are denoting up to x1 to xk vector, so I equal to 1 to k. Yi is known as the observations on 0 comma t defined by yi of t is written as h of t into xi of t. T belongs to 0 comma t. So the observed linear system is said to be, if the observed linear system is said to be observable, and yi are linearly independent in L square 0 comma t, which is known as square integrable or vector functions. So whenever xi's are linearly independent in R power n. Okay, what we have to show means, if the system is observable, we have to show that yi is linearly independent whenever xi are linearly independent. If whenever xi are linearly independent, yi are linearly independent means we have to show the system is observable. It is based on the if and only if conditions. So the solutions, first we have to take that both the cases are linearly independent, and we have to prove that the system, that the system is observable. So we take that solution xi of t linearly independent in L square integrable function, which means xi's are linearly independent. So the systems 1 and 2 are observable. If the system 1 and 2 are observable means, if we take the system as observable and then we prove that yi's are linearly independent. So for that conditions, the yi are linearly independent whenever xi's are linearly independent. So we take xi's are linearly independent, and the conditions we are assumed that observable. So yi of t, which is denoted by summation I equal to 1 ci yi of t equal to 0. So the corresponding solution is nothing but x of t equal to summation I equal to, because it is in the form of vectors, k vectors. So I equal to 1 to n ci into xi of t equal to 0. So if we put x of 0 means summation I equal to ci xi equal to 0, it will be 0, and the summation term also be 0. Okay, so if all the terms xi's are linearly independent means, xi's are linearly independent means, from the equations 4 we know that linearly independent each of the vectors is equal to 0. So c1 to ck will be 0, and we substitute c1 to ck in 0 means, which means x of t also 0. So from equation 3, we conclude that if yi are linearly independent, from equation by using c1 to ck equal to 0, y of t equal to 0 means, we conclude that yi's are linearly independent in such that of the associated observation. So converse part means we have to take that yi's are linearly independent and we have to prove the system is observable. We use the contradiction form, yi to yk are not linearly independent. So not linearly independent means they are dependent. So they are dependent in LR square 0 comma 1, letting the not all of the, which means linearly independent means all the c1 to ck equal to 0, and if it is not linearly independent means any one of them, such that not all of them are 0. So for that y of t equal to 0 means, now consider that we know the solution summation I equal to ci xi of t. So x of 0 is nothing but, x of 0 means I equal to 1, ci of xi of 0. So ci of xi, not all of them are 0. So it will remain the as it is. So here ci of x of t, that is here 0 means x of 0 is here, it will be 0 because x of 0 means xi, but all the ci's are 0 means here x of 0 equal to 0. Okay, but in the step not all the ci's are 0, so it will definitely it will have some values. So xi's are linearly, since xi's are linearly independent, so which means we assume that xi's are, we assume that y1 to yk are not linearly independent, but whenever xi's are linearly independent, our y of t will become, so summation ci xi, here it is linearly dependent, xi is also linearly dependent because we are using the contradiction form. So x of t equal to summation I equal to 1 to n c of t xi of t not equal to 0. Definitely it will not equal to 0, it has some value. So our y of t equal to, our y of t will be 0 means, but our x of t is not equal to 0. For so the system is 1 and 2 is not observable. We are taking the y of t is not linearly independent, so the system is not observable. If we take yi's are linearly independent, whenever xi's are linearly independent, the system is observable. Hope you all understand, and thank you.